Thank you so much. Thank you for showing up and coming with me to join this session. And what we plan to do today over the next 20 minutes is to really cover, there's a lot to cover about inference, but I would like to sort of tell you a little bit about how we approach open source inference from vLLM, and which is the inference engine that lets you run any large language model on data center hardware. And really there to, hopefully this will be a start and a spark of discussion and inspiration for you all. And yeah, let's get started. So what is vLLM? vLLM is a leading open source inference engine. And for those of you who don't know, inference engine is really the layer between model and hardware. It's where you take a pre-trained large language model running on data center hardware. It's an engine that generates a token one by one. What we actually see though is actually quite critical in the AI ecosystem. It turns compute into intelligence, right? And then it is vLLM from its original funding is built for production inference. vLLM is based off an algorithm called page attention, which makes large batch of sequences that do not conform to the same length in large language model processing efficient and high throughput. And over time, it has grown to become the open standard with Apache 2 and hosted under the PyTorch Foundation. We have over 2,000 contributors. Actually, today just updated, more than 3,000 contributors that are actively supporting this project by submitting pull requests on GitHub, adding new model support, fixing bugs, adding new hardware support, as well as just generally trying to make this engine more and more productive and useful for the daily use of how people are deploying large language model. Now, the bigger question we would like to ask with our view stemming from the open source engine point of view is how do we operate? What is operation and what does operating AI system really means? And what are the pieces beyond just the arithmetic or architecture? So this is really breaking down into three questions from where vLLM sits. That is model, workloads, and hardware. The model are evolving over time. From 3 years ago, when we are looking at OPT and Llama and Mistral, and then there's a DeepSeek moment. Of course, a lot more architecture has emerged over time. vLLM today supports more than 1,000 model architecture and a lot more through the extensive ecosystem in Hugging Face. And what model architecture do you use? How big do you want to use? Do you want to go as small as a 30 million parameter model, which vLLM does serve, all the way up to close to 3 trillion parameter model, that's like Kimi K3. And the other part, of course, is we have a wide range of model delivering different kind of Pareto of efficiency and accuracy front, and then you should serve them on hardware. For hardware, we are really focused on silicons and which type of architecture. vLLM today, we're not at 1,000 silicons yet, but we're at more than 100 different accelerator types. Here, for example, we differentiate AMD MI 300, 325, 350, and then we've announced 400 in different series as different accelerator type. The rationale here is every single chip is built differently. Every single chip has different instruction set architecture. It has different ways and optimization. Even just two of the same chip, if they have different memory, that requires a different optimization to fit different models. And if you can just think about this 1,000 model and few hundred architecture, this a few hundred hardware, this is already big combination space. But our problem doesn't stop there. The way people are thinking about operating the model today, operating the AI system, is about workloads. That is, what is a characteristic? Again, 3 years ago is about completing a sentence, autocomplete, summarization, ChatGPT style workload. Today, it evolves into agentic, specialized like voice, and a lot more productive usage. And all of this are changing the way inference works today. And from the vLLM community, we get to see all of these are diversifying and building the unified layer to serve all that. Let's actually dive into one by one a little bit more. So on the model are becoming more diverse. I'll get a little bit technical here. What Kimi K3 just launched. Kimi K3 is a 2.8 trillion parameter MOE. It features attention paradigm of KDA. GLM 5.2, which recently has been occupying the mind of many people as a practical replacement or like open weight model replacement for a lot of coding agent workload. I have seen here people moving from Claude to GLM successfully. And it is a 744 billion parameter MOE. It features DeepSeek sparse attention. DeepSeek own model, DeepSeek v4, is a smaller MOE, has two different kinds of attention. Qwen has yet another kind of attention, a lot smaller, and Minimax is using their own variant. The reason I mention attention beyond just the difference in model size here is every single model is very, very different from each other. The rationale is all these open weight models today, they have all of their own design choices. We have a lot of engineers in this room. When you design a system, when you are writing a design doc, you think about trade-off, you're thinking about design choices. Just when you're designing the model architecture, it's exactly the same. Every single attention paradigm is a new innovation, and this new innovation warrants different kind of system optimization overall in the vLLM ecosystem. So what does that mean? In vLLM, we actually adapt to all these models what we call day zero model release process. So before the model is fully open weight, we actually directly work with the model lab to study the attention pattern, study the architecture, make sure you can run it accurately and performantly directly when the model is released. We call it day zero because when the model is released, you already have it. And we also adapt to the size and parallelization strategies. We support many kind of dimensional parallelization, tensor parallel, pipeline parallel, expert data parallel, context and sequence parallel. All these parallelization can be combined and multiplexed together with any sized model in vLLM. So it's becoming this operating system that you can pick and choose what are the optimization you want to use. Different attention types, we have different specialized attention kernel. And finally, optimization for long context, optimization for different kinds of modality of output and processor is very different. One example is across all of these models, not all models are just text in, text out. A lot of these models have native vision capabilities. What does that mean is you can take a screenshot and then tell the model to implement it exactly, maybe the front-end coding or like debugging something. They can understand the image, perform the OCR, and understanding the layout and color and everything natively. And processing that is not just a original inference engine problem 3 years ago. Rather, how do you handle vision? How do you handle video? How do you handle audio? And how do you handle a mix of those? Becoming quite an interesting challenge for us. Now onto the workload. What we're seeing this year is workload is drastically diversifying. It comes from single-turn chat into an agentic loop. And what does that mean is you are no longer just handling prompt in, prompt out, like request in, request out. We're really focused on multi-turn. What does that mean is previously, inference engine are looking at cache hit rate of 10%, 50%, 60%. Today, the cache hit rate of many systems is at least 80%, because if you think about your session with Codex and Claude, it takes more than 20, 30, hundreds of turns for it to happen. And every single turn, we will want the prefix of context to be cached. Additionally, multimodality and non-context warrant different kinds of optimization when it becomes a 1 million context window. And then as additional, how do you use multiple models to orchestrate together with a plan, act, and observe loop. And in vLLM, we have a suite of optimizations I just covered. But one interesting, for example, is how, even as basic of how do you handle tool calling correctly. When the model say, I want to call a bash command, or I want to do a file edit, can the model accurately say and be able to output this? Because outputting the right structure output is not a simple task. Models are fundamentally non-deterministic, and in vLLM, we have a whole suite of parsing logic, structure output enforcement to make sure the model can have a high success rate, and we directly work with all the model providers on that. Now, another point of thinking about workload is a Pareto curve. So what I'm showing here is on semi-analysis inference X dashboard, and it's showing one of the curve for MI355 for Minimax M3. And it's a little bit hard to see, but I'll contextualize it for you. And this has been sort of the curve that the vLLM developer are looking at, as well as together with our model and ecosystem partners. On the y-axis is throughput. It means the number of tokens it can be processed per GPUs. So that means the higher it goes, the more productive potentially the system can become. On the x-axis is interactivity. It means per user is tokens per second generated. And if you're a user, right, what you actually really want is to be a lower right, to the right, because you want not just 5 tokens per second for the model to generate, rather 100, 200, 1,000 tokens per second, because that means the fastest output. But not all model provider or inference engine will let you do that. The rationale here is cost, because the more you push on a single user interactivity, the less you can give for throughput. And this is where the inference care paradigm with semi-analysis is quite impactful here, because it's not a better or worse problem. It is a problem of which point do you want to choose for productive inference. And this is a Pareto curve. That means, of course, it's better to go top right, but in actuality, we're making real system trade-off here. And so in vLLM, you can explore any points in this Pareto curve that will satisfy the economic requirements, SLA, and everything you need. And finally, on hardware, our reflection here is we need to get ahead of ourselves. So bringing up a new generation hardware takes tremendous effort in partnership with the open source community and the hardware companies. And so what we're doing with AMD recently is an effort called Day Zero hardware bring up. So with Helios and 400 series, we're able to see vLLM running on it directly day zero. And we see the effect, we see the performance being optimized over time, and we want to make sure when you get the chip, it already works. vLLM should be already there and then be able to productively serve the tokens. We're also working with Aider-tuned kernels. That means for the hardware, every single generation chip, as I mentioned, warrants a different kinds of optimization. So for different attention I talked about before, there are different kinds of attention kernels. And in fact, there's throughput optimized attention kernel and there's latency optimized attention kernel. So the way you interact with hardware, in the future, we believe even for every point on the Pareto curve, that warrants a different kinds of kernel design potentially. That will let you choose and get the best out of the chip. And we directly work with AMD here on Aider, Atom, and many, many other libraries, ensuring that we can make the best, get the best out of the hardware. And finally is the disaggregated serving. Hardware today are designed for large-scale disaggregated serving. Disaggregated serving means in order to serve a request, you are not just running it one pass through an inference engine running on multiple GPUs. Rather, you run prefill in some nodes and decode in some nodes. Or potentially, if you have a multimodal encoder, you do what we call EPD segregation. And for that, you are actually, for a single request, running through 3 separate stages of the pipeline. That creates extra complexity, but also creates extra opportunities. So with Helios, we're able to run large-scale disaggregated serving with vLLM router and LMD, and this proves to be quite effective, improving the overall system performance and throughput. And you'll soon see vLLM disaggregated serving on InferenceX dashboard from semi-analysis as well. And fundamentally, what we care about is how do we bring open source intelligence efficiently to everybody? Our mission really is to ensure everybody can serve the model cheaply. Now, one way actually is to run distillation on Arrow loop. So vLLM doesn't exactly train the model. However, vLLM has been the leading rule-out engine for generation. So behind a lot of popular library like Virl, Vime, and a lot more, and PrimeRL, vLLM can run on AMD chips directly out of the box. And we also have optimization for live weight updates and training inference consistency, as well as different support, so that there's actually a large class of inference being done in the training process today, and vLLM also cover that. So all around, like this kind of should give you a bird's eye view of how vLLM today is working and addressing challenges in 2026. And another major point here is with open source, open weight model, with open source, open weight inference engine like vLLM, and you can actually lower the cost of inference and doing so in a very cost-effective manner. What we're showing is a rough calculation of blended cost. Of course, you should be able to do your own math, and this is actually showing up from semi-analysis again. They're doing very amazing work, sort of demonstrating this point. If you take the blended cost of input token, blended cost of output token, take the average market price of AMD MI350X. serving DBC v4, KMK 2.6, Minimax M3, which are cost competitive on Arena leaderboard with many of the smaller models today, you can actually just get drastically cheaper tokens. And this, when you are owning your own intelligence and lowering the cost and be effective about that, is where the future will lie with open source. And finally, there's a lot of misconception about open source engine doesn't mean production. vLLM actually is built around production readiness from out of the gate. The reason here is when we build as a research project, we actually study what people need in production. The whole page attention paper comes about when we try to serve a large model using older technologies in production and then making sure it can meet the production standard. So how do we do it here? We make sure that API can be dropped in so people can easily migrate. We make sure there's a rigorous correctness process. We make a release every 2 weeks. Every 2 weeks, we make significant extensive tests on AMD and for other hardware as well. And finally, we have a well-governed release and security process. So that means across all the changes, how do we govern the changes from 3,000 contributors? Is this large-scale, almost potentially one of the largest open source project out there? What we do is rigorous testing, rigorous security, disclosure policies, and vulnerability program, and making sure that when you install the software, you are safe to use it, and you can operate it easily, and then you can ensure it's correct and has little regressions. Of course, not saying we're perfect here, but we're really trying to make this open source software, which will be the open source standard for inference today, to be a lot similar to how an operating system does it, how Kubernetes does it, and any project we respect to. What is ahead of us? What is on the roadmap? So vLLM focusing right now is actually quite diverse. So I encourage you to go to roadmap.vlm.ai to study it further. But just for today, for Q3, we're working on the core changes we call Model Runner v2 and flat model interface. These, I won't go into too much in detail, but long and short of it is we are rewriting the core of vLLM over and over and over again to account for new model architecture, new hardware architecture, and new workloads. We focus a lot on scale out. So with LMD and then other disaggregated inference engines, we ensure vLLM have broad compatibility and native integration. We recently shipped a Rust-based front-end. vLLM from its beginning has been a Python-based project, even though we directly call into PyTorch and CUDA and HIP. But we have been seeing the issue with Python, so as well as production readiness of it. So we have built a Rust frontend recently, and then shipping out and improving that, and we're planning to make it the default going forward. And finally, I will leave you with this kind of projection with vLLM, that is, we're going faster and faster and faster. With a technique called speculative decoding, which we thought it'll give you a good 1 to 2x speed up. But now we can do a lot more. And we now have a line assigned for any model to go to 1,000 tokens per second on reasonable hardware serving it. That means you can economically get a faster fast mode than any fast mode you can get on just like 8x or like 16x GPUs cluster. This is a combination of spectacle algorithm as well as TileRT, which resembles a mega kernel approach to make sure the inference runs faster and faster. So that will quickly, and we're excited to get it to the hands of you. And that will be all. Thank you so much for tuning in and hearing me cover this. For questions, and I will be taking it in the expo hall. So we have in the middle of the expo hall, there's a booth, say Infrac vLLM. So looking forward to see you there. Thank you so much.